Hello everyone, today we learn about time independent Schrodinger wave equation. Without wasting any time, let's begin. Time independent Schrodinger equation, which relates the time derivative of wave function side the kinetic energy term of the wave function, gives this Laplacian term. Really just the second derivative x if we are doing one dimensional problem plus the potential energy term given by the potential operator V operating on, say, we will start solution by assuming that V is only a function of x and that it doesn't depend on time. This is an assumption that will carry forward for most of the series. When we make this assumption, our Schrodinger equation we get reduced to the following, which I will call equation 1. Now our goal here is to solve the partial differential equation, but how do we that? Well, use something called separation variable. You are probably familiar on partial differential equations. Variables, the idea to write the solution side as product of two function, one of depend on only one of the time independent variable x while the other only depends on t. But if you are paying attention in my PDE series, you will know that certain condition before we can use separation of variables. One of these condition that PDE we are solving must be linear and homogeneous. If you look at the Schrodinger equation, we are solving through the PDF linear in the wave function. We are solving for the its linear inside. There is no psi squared or derivative of Saber squared also. Homogeneous, there's no constant or function being added that doesn't include the other condition of separation of variables is that the boundary condition on this PDE are also linear and homogeneous. Boundary condition not yet at least, so how can we use separation of variable? Are we just guess that the boundary condition we will linear and homogeneous? Well, kind of this is where the normalization condition comes in. Wave function must be normalized. The integral of their magnitude squared overall space must be 1. This because wave function are related to probability distribution of this space or particle wave occupies. Now if wave function is square integrable to the integral shown in by normalized condition, this integral its finite must follow that v function approaches 0, x approaches negative, positive, infinity. Approach 0, then its integral would not be finite. Discuss this already in my very introduce Schrodinger equation. Of course, there are expectation to this rule right here, but those expectation are exotic mathematical function hardly ever come in physical anyway. This rule must be true, then at some point at very boundaries our domain psy must be 0, will be homogeneous because I must become homogeneous at very ends and domain by virtue of the normalization condition. This may not be most justification for why the boundary condition for Schrodinger equation are homogeneous. I can come with, I think so, better alternative, just separation of variable, which a lot books the now we have established the separation of variables is valid and applicable in the context of equation. Let us use solve our PD. We will start by finding the time derivative of our separable solution. The time derivative of psi is the time derivative of small psi times tau, but since small psi is constant in time, we can take out often small psi time the ordinary derivative of tau with respect to t. Next we will find the second derivative x over psi. The idea here is similar. The second derivative of psi, second derivative small psi time tau, but in case psi tau constant with respect to x, we can out tau from the derivative expression. We will left and tau times second ordinary derivative of small psi with respect to x. Let's now our second derivation x our first derivative time our solution psi and substitute time, then all terms separated function tau and small psi, then we perform substitution. We will end up, let's now divide both sides by small psi time tau to end up with the following the reason. Officially separate the variables x and t different sides of the equation. This is where we have to be a bit clever. The left side only function of time t, well this side only function of the position. x. Now if I change the tau is a function of time could change, and the derivative of tau, which is also function of time, could change. However, changing time doesn't change anything on right hand side, because there nothing the right hand side which is time dependent. Individual terms left might. Then combination doesn't change, because the combination has to equal the right hand side which is constant time. Similarly, if I change the position x, then the left hand side of the equation stay constant, which means that right hand side must also remains constant. So changing either x or t doesn't affect either half of the equation. So we say both how constant you can prove yourself by taking derivative of both sides with respect to x and t. Show that the whole equation actually equal a constant, and this constant I am going to call I will now be solving the time part of the separation Schrodinger equation. I will move at known tau terms -1. It means that moving I got numerator on the right hand side. We will create negative sign out front. That means 1 over tau times d, and dt negative is over h bar. You can quite easily solve the equation by moving dt to the right and integrating both sides on the left with the natural log of the absolute value of tau, and on the right we will end up negative over h bar times t plus integration constant c. If we take exponential both sides, we will find tau equals the exponential from entire right hand side. Using the sum rule of exponent, we can split exponential of sum into the product of two exponential. Now the exponential of constant c is just another constant. So eventually we will find tau of t is time exponential of negative, it's over h bar time t. Meanwhile, the differential equation involving position is the following. If I multiply both sides by small side, here what we'll get now, I'm going both to in equation, because quite special, it calls time independent Schrodinger equation. There is no dependence of the equation on time. We can only solve it through specify potential operator v. So we have stopped here. Once we solve this time independent Schrodinger and obtain a solution, small side our overall function side we will small sign x times exponential negative, that is h bar time t, of course the constant of integration. I had earlier that tau will be absorbed into small side, which is why I haven't included here. Anyway, that should do. This is the required expression of independent Schrodinger equations.